the sense that if one knew the positions and velocities of all the particles in a system at a given time, then one could predict their behavior at all subsequent times. So this is what I was mentioning with the moon. If you write down the equation for the moon as a function of the position of the moon as a function of time, then that is a pretty deterministic equation. Generally, you can generally you can then predict so this predictive nature of physics, right? I'll write down the equation for something, and that will then predict what's going to happen in the future. This is what people were used to. This is what classical physicists were used to. I'll write down the equation of the position of the moon now, and that same equation can give me, when you plug in for the time later on, it can give me the position of the moon later on, 100 years later. This is what people were used to. This is deterministic. To then go from there to quantum mechanics, where things are probabilistic, was a big jump. A big jump in their, it's an intellectual jump, right? It's this like quantum timeline jumping, basically, of like, we're not used to this, okay? So anyway, the universe running according to Newtonian physics is deterministic in the sense that if one knew the positions and velocities of all the particles in a system at a given time, then one could predict their behavior at all subsequent times. Quantum mechanics changed all that, since one of the essential components of this theory is that the principle that at a fundamental level, the behavior of particles is inherently unpredictable, hence the need to resort to calculations of probability. So how the behaviors happen at those quantum scales is totally different. The interpretation to be put on this probabilistic approach is open to considerable debate. For example, consider a system in which particles travel in a beam towards two closely separated slits. The wave function psi corresponding to this situation displays an interference pattern because the probability wave passes through both slits. So this is a very common little experiment that's done in physics classes, the double slit experiment. If the beam is powerful, it will consist of huge numbers of photons. Statistically, the photons should land on a screen behind the slits according to the probability dictated by the wave function. Since the slits set up an interference pattern, the screen will show a complicated series of bright and faint bands where the waves sometimes add up in phase and sometimes subtract because of being out of phase. This seems reasonable, but suppose we turn the beam down in power. This can be done in such a way that there is only one photon at any time traveling through the slits. So like, what if you tricked this setup and said, we will only allow one photon. One photon. Don't you be leaking anywhere else. The arrival, this can be done in a way such that there is only one photon at any time traveling through the slits. The arrival of each photon can be detected on the screen. By running the experiment for a reasonably long time, one can build up a pattern on the screen. Despite the fact that only one photon at a time is traveling through the apparatus, guess what? Guess how what? The screen still shows the pattern of fringes. So even when you reduce it down to one photon at a time, light still behaves like a wave. How? How? How does it maintain this dual nature of both a particle and wave? How? Who's going to explain it now? Right? It's like if you left this to classical physicists, what are you going to do? What are you going to do? What are you going to do? How are you going to explain this? How are you going to explain the fact that you allowed only one photon through and you still got the wave nature of light as well as the particle nature of light? There was still the dual nature of light being manifested. How? How do you explain that? Who comes to the rescue? Even though it's bizarre, uncertain